Thanks, Beth. This is a bit more of a technical talk, so I'm sorry, it probably won't be quite as exciting as the previous talk, but hopefully for those of you a bit more technically minded, it might be of interest. So I'll be talking today about flood forecasting and reliability, and I'll just start by giving some context for the work that we've done here. Basically, the main supplier of flood forecasting and warning in Australia is the Bureau of Meteorology. They've had a very long-running service for many decades, issuing flood forecasting and warning. This is a map here that shows the sites. Perhaps I'll just bring up a pointer. Where do we do it? Thanks. So this is the map of the sites where flood forecasting warning flood forecasts and warnings are issued. They offer two products: a flood watch, which is an early advice of developing situation, and a flood warning, which is when flooding is occurring or is expected to occur, so it's imminent. And this is an example of a flood warning. So you'll see it's a bunch of text. So while the models used to generate these forecasts are quantitative, the warnings are written, they're qualitative warnings using calibrated language. And the flood forecasts are generated by highly trained and experienced hydrologists who run their models in and tune their models in real time. So they're a really integral part of generating those forecasts. And not only, of course, do they issue written warnings like this on the Bureau's website, but they also can communicate directly with state emergency services personnel and other emergency services people to ensure that the forecast is conveyed in a meaningful way. So their involvement, flood forecasters' involvement in this process is really critical. More recently, the Bureau, in fact only in August this year, have released a 7-day ensemble streamflow forecasting service. So this is something that we've developed at the Bureau, at the CSIRO, in collaboration with our colleagues at the Bureau. And it's a bit different than the flood forecasting service. Firstly, it's a continually operated service. It runs all the time. And rather than putting out a flood warning like this in written language, it actually gives you the output in the form of a hydrograph. So a hydrograph is just stream flow over time. So this is a forecast. You can see here the observation running up to the forecast, and then we've got our hydrograph. And this uncertainty is derived from our ensemble. And it's this measurement of how appropriate this uncertainty is that I'm going to be talking about today. So what we want in our uncertainty is that it be as narrow as possible, so it makes decision making easy, but not overconfident. So we don't want to be cutting out possible extreme events. Now, when this forecasting service, this service was developed really for water management, not necessarily flood forecasting. But now that it's in operation, we were asked, well, can it be used by flood forecasters? Can it give them some bit of extra information that can be useful to them in issuing these flood warnings? And the first thing we considered when we did this was how we would go about looking at the reliability, like the ensemble spread for flood warning. So just a quick overview of the model chain that's used to develop the 7-day forecasts. Starts with a numerical weather prediction model, in this case the ECMWF model. Now, even fancy numerical weather prediction models like ECMWF are often biased at the scale of catchments, and the spread of their ensemble is not necessarily correct. So we apply a statistical model to correct both those things. And that produces an ensemble precipitation forecast over a catchment. Now, floods, you need rainfall, but generally for fluvial flooding, you also need a wet catchment. So we need to assess how wet the catchment is, and we do this by initializing a hydrological model. And once that's initialized, we just force it with the ensemble precipitation forecast. Now, we've got our uncertainty, as I said. Uncertainty is a crucial factor here. We've got the uncertainty of our rainfall forecast all sorted, but there's also uncertainty in the conversion of rainfall to runoff by our hydrological models. And so we have to correct that as well using a hydrological error model that we've called ERRIS, stands for Error Reduction Representation in Stages. It's not important how it works, just that it's there. And in the end, it produces our ensemble streamflow forecast. Now, an important factor of this is that we keep the quantification of uncertainty from the rainfall forecast separate from the hydrological model. So we don't just do a bulk uncertainty processor at the end. We rely on the uncertainty generated here, summing with the uncertainty here to get the ensemble reliable in the end. So I'll just briefly on reliability in the information value chain and what role it plays. Reliability is really crucial in kind of easing the flow of information through any value chain. So for flood forecasting, it means that our forecast probability should reflect flood risk. So what I mean by that is if we've got an ensemble of 100 members and 10 of those members are telling us there's a likelihood of a flood, well, then that should reflect in real life the 10% flood risk. You shouldn't need an extra expert or hydrologist to say, well, actually, I happen to know that flood system, that system underestimates the probability of floods. So I'm just going to have to I'm going to have to fudge that probability a bit. It should actually equal the flood risk. So we don't need this kind of hedging. The forecast can be used as is. So the other thing that's important about having reliability is that uncertainty can be propagated downstream. Now, in the case of streamflow forecasts, I mean that literally. In that, this is an example of one of our models that we use to generate these forecasts. So this is a catchment. That's a gauge at which a forecast is issued, and the water then flows downstream, and then a forecast is issued at a stream down here at the gauge downstream. And we can only get the uncertainty right at this point if the uncertainty is right at this point. So we have to have our uncertainty correct so that it flows downstream and we can produce a reliable hydrograph ensemble prediction at the end here. So in a similar way, we want to be able to use the outputs directly in decision models. So we don't want to have people like perhaps the Murray-Darling Basin Authority or others who use these outputs directly in their models to having to mess with them, messing with the outputs anymore. So these downstream models can be reservoir optimization models. They can be models used to optimize flooding. So this is a photo of the Barmah Forest along the Murray, and this is an ecosystem that relies on floods. And we can control flooding because there's a large dam upstream of this forest, but it's a long way upstream, so there's a lot of other stream flow that comes in downstream of the dam. So you have to coordinate any releases with forecasts. So we need models to do that, and we want to be able to use them. We want those people who use models to be able to use our outputs directly in them without having to mess with them in any way. So the problem when it comes to reliability and flood forecasting is that we can't assume that just because our forecasts are reliable overall, that when we look at all our forecasts that we've generated retrospectively, we can't assume then that a small subset of those forecasts for floods are reliable. And this is demonstrated by Thomas Hamill in a now classic paper some 20 years ago. So what we have to do then is work out a way of selecting forecasts so that just a subset of all our forecasts that are relevant to floods. Now, the conventional and traditional way of doing that is just to say, well, there was a big flood in 2012. So I'm going to go and look at generate a forecast in 2012 and see a retrospective forecast and see how we did. Now, there are a couple of problems with this. The first is that you need lots of forecasts to measure reliability. But the second thing is that this paper by Joseph Bellier and others show that you can't go and do it this way. You can't sit there and say, well, there was a flood in 1994 or a flood in 2012 and then look at the forecast for those things only. What you have to do is so-called forecast-based selection. So you need to look at what happened in the forecasts. So to do that, you need to generate a whole bunch of forecasts and then look at information in the forecast to see whether that should be included as a flood forecast or not. So I'll just talk you through a process we had for doing this kind of forecast-based selection, and it's pretty straightforward. So here is a forecast. the grey lines here are the ensemble, all the members of the ensemble, and here is some flood level that we're interested in. And because it's an ensemble forecast, a probabilistic forecast, we can convert our forecast into a probability of exceeding this level, and that's what I've given by this blue line here. And we also know that given the historical record of floods, how probable it is to exceed this flood, just if we don't know anything, like just looking at the climatological probability of exceeding a flood, and that's typically given like by an annual exceedance probability or something like that. So our theory goes that when our forecast here is telling us that the probability of exceeding a flood is much greater than the historical probability, then we say, okay, this forecast looks like there's a flood, so we're going to check whether we're going to use it, add it to our pool of forecasts that we're going to check the reliability. So this is also a possible method, this process of selection. It's also a possible method for issuing a flood watch. It's a reasonable thing to assume that if you've got a heightened probability of flood, that you might issue a flood watch. Converse is when we have a forecast that's not selected for verification, that we don't consider when we're assessing reliability. And this is the case here, that even though there's a few ensemble members, maybe a little bit difficult to see, that exceed this flood level, because it's a very large ensemble, this is 1,000 members, it makes no dent on the exceedance probability. So it's basically saying that there's very low probability that flood will be exceeded, that flood level will be exceeded. So we're not going to consider that a flood. We're not going to issue a flood watch, and therefore we're not going to look at whether that forecast is reliable or not. So just to talk you through briefly how we measure reliability. So we use a measure called the probability integral transform. And this is a measure, so that those of you who are familiar with forecast verification might have looked at spread error diagrams, or you might have looked at reliability diagrams. This measure here is widely used in the statistical literature, and it's for treating values as a continuous variable. So what we start with here is a bunch of forecasts that we've selected. So I've just made these numbers up. So this is what our forecasts look like. Because they're an ensemble forecast, we can look at the uncertainty of the forecast as a box plot here. And then only after we've selected the forecast do we look at what the observations were. And to measure a probability integral transform, we first have to do a little conversion here. We have to look at make our forecast ensemble into a cumulative frequency distribution, a CDF. And then we can basically plot where our observation falls on this CDF, and that gives us the probability integral transform. So this is kind of a fancy way of saying a rank. So we look at this, where is the rank of this forecast of this observation in this ensemble? And in this case, it's quite high. So we do this for every forecast, and what we get is, and we can then do various statistics on these. And one way of doing that is just plotting a simple histogram. And what we want to see is that our ranks, or our probability integral transforms, are uniformly distributed. When I talked about this a couple of weeks ago, I was asked about this assumption, why should it be uniformly distributed? It's not my assumption. Like, this is a very well-established principle in the measurement of reliability of predictions. So we can present that as a rank histogram, which some of you may be familiar with, or a tallogram diagram, or we can simply plot each of these values, and here I've got obviously a lot more than the 10 I've shown here, against a standard uniform distribution. And then we can use this as a nifty diagnostic to tell us something about the reliability of the appropriateness of our ensemble spread. So if our ensembles, all of a sudden I've just shifted these all up, so they're positively biased, this is what our PIT plot looks like. When they're negatively biased, it looks like this. When our ensemble spread is too narrow, it looks like this. And when it's too wide, it looks like this purple line. Sorry, that's probably too many lines, but so perfect is 1-to-1. Okay. We also usually need some other measures of our forecast quality, like accuracy and sharpness, but I won't be dwelling too much about those today. Okay. So we've got our probability integral transforms well, what can we do with them? Well, one thing that we thought about that's particularly important to flood forecasters is not just the magnitude of the peak, but also the timing of the peak. And so here is our example forecast, and we can, instead of just looking at the hydrograph as a whole, we're just going to look at the instances where peaks occurred in our forecast window of 7 days. So we can break down the forecast into just these dots here, and then we can represent those as those dots as a ensemble of peak magnitude, but also as an ensemble of peak timing. So it gives us a distribution of peak timing. And we can apply our probability integral transform just as we did before. And this gives us, just as I did before, it just shows you, this is exactly from the previous slide. With peak timing, it's a little bit trickier because there's no, if we're issuing a forecast every day, which we are, there's no reason to suppose that a peak flood would occur more often at the start or the end of a forecast than in the middle of a forecast. So these are timing errors essentially that are associated with sampling incorrectly your forecasts, which I won't dwell on too much, but it's just a slight difference. Okay, and just to show you how these measures can work, I've got a case study here for Emu Creek in the Brisbane River. It's upstream of Wivenhoe Dam, which was, for those of you who remember, the 2011 Queensland floods. That's what caused the inundation of Brisbane. And I've got two methods that I'm going to be trialling. It doesn't really matter what they are, and they're different error modelling methods. So the important thing to note about them, and they just handle this smooth conversion from the forecast to, and also so correcting errors in the early parts of the forecast, and also quantifying the uncertainty in the hydrological component of the forecast. That's what the error models do. And if you remember our probability integral transforms, and I've just called these versions ERIS A and ERIS B. Doesn't matter what they do, but the important thing to note is that ERIS B is like the improved version. And when we look at all our forecasts, not just flood forecasts, they're reliable. So you can see they follow the one-to-one line at different lead times here. Whereas ERIS B tends to become more biased, positively biased at these times. And the reason that is because the ensemble spread is too wide. So just to make that a little less abstract, I've just shown two observed events and how these different forecasting systems operate. So these were candidate methods for our forecasting system. We're trying to decide between them. And what tends to happen here is we've got an observed event here. It's very, and note that this is a different scale from here to here. And the reason it's a different scale is because the forecast that we've generated with our first forecasting method is way too wide. Too much uncertainty in this forecast. In fact, so much uncertainty that it exceeds the minor flood threshold. Whereas the actual observation, which is given by this red line, this red dot here, which is barely visible down here, is much lower. So the mean of the forecast is around 200 cubic meters per second, which is 10 times larger than it should be from the observation. So we know that ERIS A, generally, this is a problem. It tends to overestimate the uncertainty in the forecast. But the question is, does it do that for floods? And here's an example of a much larger event where the red line here, hopefully you can see that exceeds our minor flood threshold, but our system that's giving us more uncertainty is actually doing a better job than our system that's giving us less uncertainty. It's a lower peak here. So the question is, does this happen? We can't just look at one forecast. Does this happen all the time? So we generated 6,000 forecasts to check. The first thing we have to check is whether the forecast we selected using our selection method, sort of the flood watch method, how successful that was. And what I've plotted here is the frequency bias. So how many forecasts that we selected compared to how many floods there actually were. And there were 26 floods during our period. We looked at a 9-year period. But with our very poorly reliable system, we selected 2,000 forecasts. So why was that happening? Well, there was just way too many, because the ensemble's far too wide, it kept telling us there were going to be floods when there weren't. So with our better system, we select far fewer, although you'll still note 120 is too many. And that's what this frequency bias reflects. So we've calculated this at different lead times with our our poorly performing ERIS-A model, we're getting way too many forecasts selected. And that's leading to, and that's reflected in false alarms. We get way too many false alarms with ERIS-A than we do in ERIS-B. So it's not a very effective forecasting system for issuing flood watches. So the next question is, how reliable are our forecasts? Is the uncertainty spread reliable once we get to the peaks? And the answer is that yes, ERIS-B, even though that initial forecast I showed was underestimating the forecast, when we look at our 120 points here, actually they're pretty reliable. When we look at our many thousands points here, 2,000 points here, which is what's included in our initial system, it's not as good. So with peak timing, so I've also included these little insets here, which show a measure of error and a measure of sharpness. I won't talk about it too much, but basically lower is better. And our system here is also giving us lower errors. It's also giving us lower timing errors, as you can see here, so lower is better. But what it's telling us is that the peaks are predicted too early in our forecast. So generally speaking, at this stage, the forecast system is rising too fast, which is kind of unusual. Often it's rising too slow. For our poorly performed system, we get this weird S shape, which should never happen. And the reason that's happening is because we're selecting far too many floods, because our forecast uncertainty is growing too much towards the end of the forecast. I'll just skip over the next part I was going to talk about, because I think I've probably run out of time. So I just finished with a recommendation that reliability of ensemble forecasts is a really important link in the value chain, because it means you can use forecasts, the outputs from forecasts directly in downstream models, which in streamflow forecasting we're very much interested in. But we can't we can't select forecasts on the basis of observations if we want to measure reliability. So I hope I've demonstrated that today. But it does mean you're comparing different numbers of forecasts, which can lead to complications. Finally, observation-based selection is still useful, certainly for communicating forecast performance. It's far more useful to say, once you've done all your stats, it's far more useful to say, well, actually in 2012, here's an example of a big flood, and here, look at how good our forecasting system is. For communicating, I think, especially in non-technical audiences, just looking at observation-based selections is still extremely useful. And that's it. That's all I've got from today. So thanks very much.